looking at strength of materials. First of all, look at the definition of strength of materials. The definition of strength of materials. Now, the name is already telling us that we are dealing with materials, right? How strong a material can be. So now, looking at this class now, how many materials can we see in this classroom? Like looking at it, observing the environment. How many materials can you see? Can you notice? Okay, just raise up your hand and answer me if you see any material that you are familiar with or you know. Okay, anybody. It's an interactive section. I'll be asking you a question. Okay, give it to me. The what? Rod, that's metal. The rod will fall under metal, right? So we have metal, right? Metal is a material, right? All right. Any other material? We have steel under here, rod. Which other material do you have again? Eh? You have iron. Even if, what are you sitting on? You're sitting on wood now. So wood is part of the material. Wood. It can be timber. It can be different type of wood. Wood is part of the material. Which other thing are you sitting on again? Tiles. Okay, tiles. So now the tile will fall under what material? Ceramic, right? Okay, ceramic is also a material, right? Even your glass too is there. So we have different materials, and as engineers, we need to understand these materials and how they work, how they interact. You get? We need to know, because engineering is very simple. Engineering is all about problem solving. Am I right? Now, what problem can you solve is based on the field of engineering you're focusing on. As a civil engineer, my own focus is to what? Solve problem of shelter. Let me say, provide shelter for you. Design a good structure that will not fall on your head or collapse. Like this building we are in now, it was designed by a civil engineer. The architect will draw the plan and pass it down to the civil engineer to carry out structural design and analysis to make sure that the building does not fail, and also to make sure that the building is cost effective. So that's my own job as a civil engineer. Civil engineer also has water resources, where you ensure that water is being distributed for people consumption, for domestic use, also for industrial purposes. We have different forms of civil engineering. We have transportation engineering. I'm sure none of you flew here. There's no which here are we in the class. Everybody enter cab, or if you use your helicopter, it's fine by you. But that's another means. So please, engineering is very simple. Don't make it look like one hard course. For the chemical and petrochemical engineers, they also have their own responsibilities. You get? For the mechanical engineers, they have their responsibilities. The automobiles we use, now we have hybrid cars, the ones using both petrol and what we call electricity, right? So the mechanical engineer will design the car to make sure that you choose a material that is strong. You can use metal. You see, you use metal. And for you to use that metal, you have to run 1 or 2 tests. So that the knowledge of this strength of materials will help you to know what type of material to use and how strong the material is. How much force the material can resist without deformation or without deforming, right? So now, from this thing I've said, who can define strength of materials for us? Anybody? Somebody? Anybody? Strength of material definition. Anybody? All right, take note. Please help you with your writing materials. Take note, take note. The attendance is going on. Where is the attendance? Okay, please, if you have not written your name, write your name, your WhatsApp number, and your department. There's a WhatsApp group. I'll add you all to the WhatsApp group. After the class, we cannot finish everything here today. So what I'll do is, after the class, I'll also make videos. I'll record videos for you to continue. So before your exam, you'll be up and doing. I'll post the videos on the YouTube platform. There's a YouTube platform called Build and Design Academy where you can watch. Then I can also host another section, maybe a live section, maybe on WhatsApp video call, or we use Google Zoom, or we use YouTube stream, live stream, depending on how many we are and the platform, how we can contain all of us, right? So we can be up and doing. So let's go back to strength of materials. Take note. Strength of materials can be defined as the interaction. Strength of materials can be defined as the interaction between external load, the interaction between external load and you can put the interaction between external load slash force, load or force, they are the same thing. External load or force and the internally generated forces and the internally generated forces. Where is your writing material? Bring out your notes, right? And the internally generated forces of adhesion and cohesion. And the internally generated forces of adhesion and cohesion. That's my own definition. You know, definition is, it can vary. If you open your dictionary now and you say, what is a ball? They will give you different definition, right? Adhesion and cohesion. Yes, the internally generated forces of adhesion and cohesion. So that's the definition of strength of material. Very simple, right? So next up, I will introduce you to some terminologies in strength of materials. Terminologies in strength of materials. One thing about engineering is that before you study any course, you need to familiarize yourself with terminology because you're a professional or you're a professional to be. So you cannot be using a layman's English when you're dealing with professional work. You need to use the engineering term. You get? So now I'll introduce you to some terms we'll be using frequently. You'll be seeing them as you are going. So the first one we have on the list, okay, we have defined strength of materials, right? So now terminologies. So for terminologies, the first one we'll be looking at is what we call rigidity. Yes. I'm sure most of you already know what rigidity is. So let me just refresh your memory. Please, if anybody knows the definition, you can help us. Rigidity, anybody in the house? Anybody? All right, so let me explain. Are you ready? Okay, take down. Rigidity is the ability of a material. Rigidity is the ability of a material to resist deformation from an applied load or force. Rigidity is the ability for a material to resist deformation from an applied load or force. All right, did you get it? Okay. These definitions are very simple, so you need to familiarize with them so you can understand what you're doing. You get? So that is rigidity. Now, let's take for instance, this is a material, right? They designed this material in a way that if you stand on this wood now, it will not break, like it will not fall immediately. There are forces acting on it, resisting that your force that's coming on it. Yes? This is support reaction. That's why you see this column. They call it column in engineering or pillar. But this is a steel structure. So it's helping to create supporting forces. So when you exert force on this material, it will be able to resist deformation. You see, no matter how strong you are, I'm not sure you can blow this thing to break once. You injure yourself, you fracture your hand. So that's rigidity. Another thing we'll look at is elasticity. All right. This is anybody with rubber band here? Or anything that can expand and come back to its original form? Anybody? Okay, something like this now. But if I drag this thing more than its elastic limit, it's going to fracture. It's going to cut, right? So I cannot use this one. So the elastic limit of this one is very small. You get? So now, elasticity, take down. Elasticity is a characteristics or is the ability of a material to return to its original length upon the removal of the applied force. Elasticity is the ability for a material to return to its original length upon the removal of the applied force. For example, a rubber band or a rubber ring, whatever they call it in your own local, what they call, dialect. So if you drag the rubber band, you see that it will be expanding. It will expand until you release it, then to come back to its size. So that's elasticity. That material can be called an elastic material. So we have some materials that are not elastic, like your breakable plate. There's no way you drag it now. If you just, it's very, what I call it, fragile. Those are not type of non-elastic materials. We have elastic materials, we have non-elastic materials. Remember, this course is about material. We are studying materials, different materials, like wood, glass, and the rest. So now this material, metal, is it elastic or not? Can you exercise, can you define a metal as an elastic material or not? No, it can be an elastic material. If heat is applied to it, it will expand. Yes, it can deform. But I'm not sure it will return back to its original length. It will not, right? What about wood? Same thing. Ceramic, glass. So someone should mention one material that can expand and contract. Any idea? Eh? Rubber. Okay, let's write rubber. Rubber band, I mean rubber, which one? So this is an example of a material that can expand and what? Contract. All right, so let's look at the next thing we have. The next term you should familiarize yourself with is called stress. Stress. Most of you, after a very long day, you say, Omo, I don't tire, I'm stressed out. Why do you used to say that statement? Like literally, why do you say I'm stressed out? What happened? Can anybody explain to us what happened? Why we say we are stressed out? Anybody, any idea? So, you exhausted your energy, right? Yes. So, you have exhausted your energy. So, in the morning, I'm sure your energy level was very high. As the day is going, they are teaching you, your energy level is being depleted, is reducing, until you get fed up and you say, oh, I don't tire, I'm stressed out. So at that point, you cannot take anything again. Anything they teach you will not enter. It will be standing comb, it will go back to bounce. So that is what stress is. But that's not what stress is in strength of materials. We'll take note. Stress in strength of materials, are you ready? Take note. Stress can be defined as the force applied on a given body over the area, or you can say force per area. That's stress. Let's say this is the body you want to deform now. This part, let me just draw it on the board. So now, you're applying a force on this body, right? It's something they call UDL. You see that it will spread. The force will just spread on the body. So now this area, the force, you can put P, as the force or the load, or you can use F if you like, over this area is called what? Stress. This is a two-dimensional drawing. This is a two-dimensional drawing, right? So you are not seeing the third part. You know the two-dimensional drawing is a 2D drawing. You can only see 2 points of it, right? You only see it from this side or from this side. But 3-dimensional, you can see it from here, you can see it from here, you can see it from this side. So stress is simply what? Let me clean this part so I can write it on the board. Should I clean here or I should clean? Let me clean here. Now, take note. There's a Greek symbol that we use to represent stress called what? Sigma. This is the Greek symbol for stress. And we can say sigma mathematically is equal to what? Force over what? Area. Let me write it down. Force over area. And force, who knows the SI unit for force? Newton. Now, this is Newton, right? Or Newton or, you know, area is length times length. And length is in meters. Length times breadth, sorry. And length is in meters, breadth is in meters. So it will be what? Meter square, right? But now, I want to take us back to this force. Take note. For force now, right? Force is equal to what? MA, right? You can also say force is equal to mg, right? Thank you. Now, this now will be written as what? Newton, right? This one can be written as kilogram meter per second square. Do you know why one is in Newton, one is in kilogram Newton per second square? Let me explain to you why. I'm sure most of you already know, but let me just explain. Now, let's say this is a car. Please forgive my drawing if it's not fine. Right? You manage, I beg. Yakub will manage. So this is a car, right? This is a car. Which car is this? Benz. Lamborghini, Bentley, Rolls Royce, depending on. And this car is moving in a linear motion, right? Now, this is a car, right? It's moving in a linear motion. And we know that acceleration is simply what? Change in velocity over time, right? And we know that velocity is equals to what? Displacement over what? Time. I'm taking it to physics now. We'll come back to center of materials very soon. Just exercise a bit of patience with me. Now, this is displacement over time. And displacement over time is what? Meters over second, right? I'm bringing you back. I'm bringing you back. Now, do you know the difference between displacement and distance? Do you know the difference between displacement and distance? Okay, let me take you back again. I'm still carrying you back. You know, physics and maths, they are connected. This is distance, right? This is what? This is displacement. I want you to understand what you're doing, not just doing it or cramming formulas. Now, distance, let's say this is a body, right? And this is a human being standing here. And this is another body. And this is another human being standing here. Now, if I ask you, which direction is this guy moving? Will you be able to know the direction? You will not, like, this guy is moving now. Can you know the direction he's moving towards? Is he going towards this direction or this direction? You will not be able to define it, right? What about this one? He's going towards this direction, right? So we said now this guy, right, covered, let's say 10 meters. The distance covered was 10 meters. Why this guy now? We'll say he's covering 10 meters east. Right? So now for distance, take note, distance is a scalar quantity. And when you talk about scalar quantities, you're talking about magnitude, like measurement. Now you've measured the distance he has covered, and this is the distance he has covered. This is the magnitude, 10 meters, right? But we don't know the direction. Why for displacement is a vector quantity. And a vector quantity, you consider both the what? Magnitude and the what? Direction. That's the difference between what? Distance and displacement. Displacement has direction, distance does not have direction. That's why we have 10 meter what? East. You know, this is what? North, this is south, this is west, and this is what? East. So the body was moving towards the east. That's why we call it what? 10 meter east. Now, taking it to velocity. You know what is velocity, right? Displacement over time. Let me slow down. Do you know what speed is? Speed is what? Distance over time. They are different. Speed, distance over what? Time. So speed is also a scalar quantity because you're just moving, but you don't know the direction. Now, displacement is, velocity is displacement over time. So this is a vector quantity. Now, we know that velocity is meters per second, and acceleration is what? Velocity over time. So if we say acceleration is velocity over time, and velocity is meter per second, then time is in seconds. This v now, that's meters per second, and time is in seconds, right? So it will now be what? Meters per second divided by second, which will now give us what? Meters per second times 1 over second. So seconds times seconds will give us what? Second square, and what? Meter times 1 will give us meter. So this is acceleration. Now, why we do not say, why we said mass times acceleration, kilogram meter per second? Because this one now is in a linear direction. It's moving, but force of gravity is not acting on this car. But let's say a body or a ball is dropped from a given height. Right? A ball is dropped from a given height. And this is the mass of the ball, right? And we know that gravity is going to affect this ball. So gravity is going to replace this acceleration, right? So that's why you see that this one, m times g, is in Newton. And why this one, m times a, is in kilogram meter per second square. That's just the difference. That's why you see that force has two different, what they call, units, SI units. I know most of you know this already, right? But you don't know why it's like this. So I just explain. So now let's go back to strength of materials. Strength of material, where do we stop? We stop at force, right? No, we stop at stress, sorry. Stress. So we say stress is what? Have you taken notes? Sorry, have you taken it down? You've taken it down. All right. So I can clean this part too. Okay, we'll get there. So now we say that stress is equal to force over area, right? And force over area is what? Newton per meter. Or you can write it as kilogram meter per second square over area, anyone you like. So this is the SI unit. Newton per meter square. So now the next thing we should look at is what? Strain. Strain. We are still on that terminologies, right? Strain. So for strain, take note the definition of strain. Now, strain can be defined as the ratio of elongation or contraction in bracket deformation. Strain can be defined as the ratio of elongation or contraction in bracket deformation of a body. Strain can be defined as the ratio of elongation or contraction in bracket deformation of a body over the original length. Over the original what? Length. So now, for strain, For strain, for strain, the SI unit of strain, or the Greek word for strain, is called epsilon. See the sign here, epsilon. Epsilon. And we say that mathematically, epsilon is equals to what? The elongation or contraction, that's the change in length, over the what? Original length. The change in length over the what? Original length. And we know that the change in length is measured in what? Meters. The original length is measured in meters. So meters will cancel out meters. And the SI unit will be what? Dimensionless. Dimensionless. Are you following? All right, so let's move to the next thing. We've talked about rigidity, we've talked about elasticity, we've talked about stress, we've talked about strain. So now let's look at number 5. Let's talk about deformation. We've been hearing the word deformation. So deformation can either be an elongation or a contraction, that's reduction. Now, for an elongation is simply, are you here? Let me allow you to write small. Elongation of a material, I'll keep saying this is strength of material. So anything we are talking about materials, the materials we use for designing in engineering, the materials we use for construction in engineering. So materials, they have like how many materials? They have so many materials, even the new ones that are being made by man. You know, they are enhancing our materials, making them stronger, more durable. So strength of materials is simply the study of different materials and how they respond to forces when forces are acting on them, and how they can resist those forces. You get? So now elongation is simply what? The increase of a material, the increase in length of a material or dimension of a material. That is what elongation is. Why are you writing? Take note. Elongation is the increase in length of a material. The increase in length of a material. Elongation is the increase in length of a material, while contraction, or we call it reduction, is the opposite, the decrease in length of a material. So moving forward, let's look at another terminology. Have you heard of Hooke's law before? So what is Hooke's law? Let's look at Hooke's law. Number 6, Hooke's law. Hooke's law. Any idea what Hooke's law is? Anybody? Hooke's law. You know, Hooke's law has, you can define Hooke's law in 2 forms, depending on what you're talking about, right? So, take down Hooke's law in terms of force and extension. Hooke's law states that the elongation of a material is proportional to the applied force. The elongation of a material is proportional to the applied force. Very simple definition. All these definitions, we are trying to make them as short as possible, and so you can understand it and you can recall it. Hooke's law says that the elongation of a material is directly proportional to the applied force. But mathematically, it is written as F is proportional to E. But in the definition, it is the reverse. So now, for this, it's in terms of force and extension. Now, if we remove this proportionality sign, we know that we always have a constant, right? So now it will now be what? F is equals to what? K E, where K is the stiffness of the material. Where K is the what? Stiffness of the material. F is the force, where F is equals to the force. K is equals to the stiffness of the material. And E is the what? Elongation. As the increase in length. Elongation, take note, elongation is the same thing as what? Change in length. Take note of this, please. The same thing as change in what? Length. That's the increase in length. Still on Young modulus. Okay, write down, write down, write down, write down. Are you done writing? Okay. Still on Young modulus. Still on Hooke's law. Sorry, I say Young modulus. Still on Hooke's law. Another definition of Hooke's law. Still on Hooke's law. Another definition of Hooke's law is in terms of stress and what? Strain. In terms of what? Stress and what? Strain. Now, in terms of stress and strain, Hooke's law states that the strain of a body or the deformation of a body caused by the strain is due to the stress applied on that material. You know, we're talking about a material, right? So just write like strain is proportional to the stress applied on a body. Write it like that. So for Hooke's law, the next one, the definition is reversal, but if you write it mathematically, stress is equals to what? Strain. And we know that the symbol for stress is what? Sigma, right? So if we say sigma is proportional to strain, the symbol for strain is what? Epsilon, right? Now, if we remove the proportionality sign, right, this sign, we'll have a constant, right? So we say that sigma is equals to the proportionality sign, we now have a constant. So the constant will be E, capital letter E, times what? Epsilon. Are you seeing it? Where this is our what? Stress, where sigma is equals to the stress, E is equals to the Young's modulus, and epsilon strain is equals to what? Strain. Epsilon is equals to what? Strain. So we can say that Young modulus E will be equals to what? Stress over what? Strain. You can say that Young modulus E is equals to what? Stress over strain. Why I'm doing this is to show you how easy strength of material is. That you'll be comfortable. So when we go to the hard part, you will not run away. Strength of material, like I said, is a very easy course. But there's a part that is not that easy. It can be easy, it can be hard, depending on how you look at it. So let's go. Now, moving on, let's solve an example. Let's solve an example. Have you finished taking notes? Let's solve an example. Let's solve an example. Okay, once is let's say 12 o'clock or 12:30, which one? We'll go on our first break. Which one do you prefer? 12:30 or 12 o'clock? Let's do a vote. If you want 12 o'clock, raise up your hand. 1, 2, 3. If you want 12:30, raise up your hand. 1, 2, 3, 4, 5. So the eyes have it, right? All right, so we'll use 12:30. Okay, let's solve some questions. Let's solve some examples. Example number 1. Let me look for some examples from past question or so. Let me see if there's a past question here. Okay, before we solve an example, because before we solve an example, let me show you something. Before we solve an example, because we'll use it in our example. Now look at this. Now this is Young modulus, right? Now we can expand it. We can say that Young modulus is equals to what? Stress over strain, right? And we know that stress is equals to force over area, right? And we know that epsilon strain is equals to what? Change in length over original length. And I told you that change in length is also referred to as what? Elongation, right? E. So we can represent this as what? E. Let's use E. So now, if we bring it out, it will now be what? Force over area divided by elongation over original length. Right? So now, if we want to remove that division sign, we will have that Young modulus E will be equals to what? Force over area times, for that, we will now what? Invert. The denominator will come to the numerator, and the numerator will come back to the denominator. So we have what? Length over what? Elongation, right? Which will give us what? F times L will give us what? FL. A times E will give us what? AE. Right? So now we have that Young modulus is equals to what? FL over what? AE. Please take note. But we need to solve this example we're about to solve. Now let's make E the subject of the formula here. So we can also know what elongation is mathematically, right? So if we want to make E subject of the formula, what do we do here? Our mathematicians in the house. We cross multiply, right? So when we cross multiply, E will times AE to have what? EA what? E is equals to what? FL will times 1 to have what? FL. Now, our mathematicians in the house, if we want to proceed, what do we do next? On the hot, who got A in maths? Shout there, congratulations. Who else? Who got B? Congrats. Wow, we have smart students. What about C? D. Any D in the house? E. F. Why is it that some people are not raising their hands for any of them? I don't understand. Have you not write the exam? Okay, I'm not seeing your results. You not get the question. Okay, sorry. I said, who got A in their mathematics exam? Which one? What did you get? B. And you did not raise your hand now. I was wondering whether you did not write the exam. I mean, are you set to the exam? So let's proceed. We divide both sides by what? EA. so that we can cancel out. EA will cancel out EA. We'll be left with E, that's elongation, equals to what? Force over length all over EA. So let's proceed to our example. Let's run. All right, the example, take note. I will not write down the example. I will just solve direct. I will just read it out. So take note. Are you hearing me? All right, are you ready? Let's go. He said, a square steel rod, are you there? 80 millimeters by 80 millimeters. When I say by 80 millimeters, I do not say by, B-U-Y-O. It's not by you. I do not say B-Y-O. I said by. By in engineering is represented as X, like multiplication. You get? It's not by like B-U-Y or B-Y. So please take note. When I say 80 millimeters by 80 millimeters, I simply mean 80 times 80 millimeters. So let's continue. So a square steel rod, 80 millimeters by 80 millimeters, is used to carry an axial load. A square steel rod, 40 millimeters, 80 millimeters by 80 millimeters, is used to carry an axial load of 400 kilonewton. Are you there? Calculate the shortening in length of 200 millimeters. Calculate the shortening in length of 200 millimeters if the Young modulus is, are you there? You're not there. Where are you lost? Okay. Calculate the shortening in length. Calculate the shortening in length of 200 millimeters if the Young modulus is 8.56, 8.56, the Young modulus E is equals to what? 8.56 times 10 raised to power 8 kilonewton per meter what? Square. To solve, we say the axial load is equals to what? 400 what? Kilonewton, right? And we have the shortening in length as what? 200 millimeters, right? All right, so now I want to ask a question before I write what that shortening in length is. The shortening in length, is it the original length or the elongation? Eh? You say what? Who else? So elongation, people that said elongation, how many of you? How many? Raise your hand, let me count. Okay. All right, the shortening in length, they say we should calculate the shortening in length. The shortening in length is the elongation. That's what we are calculating for. While this now that they gave to us is the what? Original what? Length. Please take note. Look at your question line by line. Look at what they say you should calculate. Calculate the what? Shortening in length. That is, they say you should find the what? Elongation. So now, this is the original length. So the shortening in length, which is the elongation, is what? Unknown, right? We don't know the elongation. Okay. Now, I told you something about deformation, right? Deformation, it can either be elongation or what? Contraction. Now, for this thing now, the original sign is change in length. So, change in length can either be what? Elongation or what? Contraction. That's why we're using E. So don't be confused. I know what you're asking. So but don't confuse yourself, please. Just take it as that E is what? Change in length. This is change in length. But I'm just calling it elongation. Let's call it change in length so you will not be confused. So now what do we do? What's the first step to handle this question? What's the first step? Any idea? Eh? He said what? We'll bring out what? Who else? He said what? Convert the original length to meter. We'll bring out the formula. Who else? People should think like engineers. You're engineers. You are the future of tomorrow, right? So you start now. Yeah. Who else? Who else is thinking here? Okay. Okay, so I like it that people have the idea of what we are going to do. So solution. I love the fact that you have the idea of what you're about to do. Now, in the exam condition, why you lose your marks is very simple. You know the answer, but you're in a rush to submit and farm aura. You want to tell everybody that you're the first to finish, right? You will not skip all these things. You will skip your formula. You just go and put in the values like that. You skip conversion, skip everything. There's what they call marking scheme. Have you guys heard about marking scheme before? Marking scheme. So now, when they give you a question like that, I did not write the question, right? I just say writing the parameters. So your exam, that's what you start with. Just write given. Once you write given, and you start listing out all these parameters, this thing alone that you did here can give you 5 marks out of the 14 marks. But most questions are 14 marks for a complete question. They tell you to answer 4 questions. So now someone should punch 14 times 4. How many marks is there? Some of them will tell you answer 5 questions, right? That's for 3-unit course. This for 2-unit course. How many will you get? 14 times 5. 70, right? Thank you. So you're getting 70, right? And your CA is what? 30. So inside these 70, if you can struggle for 60 inside the hall, you are sure that even without coming to class, but you come to class because attendance is compulsory. Even without this CA, without writing tests or anything, you still pass. So passing your exam is not that hard. You just need to understand all this logic, all these things, so you know how you strike. Because some people, you write tests, you now get 1/30. Let's say physics test. Some people get half. Some people get 2.5, 3. You will not be scared that you fail. You will not fail anything. No. You see that if you struggle very well, you still get your B. You still get B. You get. So that's how it is. Don't be scared when you make mistake or when you now fail. You now feel like that's the end. No, it's not like that. You can leave your CA. You still get your B inside the hall. You still get your C if you know how to attack the questions. So now this is like the marking scheme. First step, list out your parameters. The next step, you convert them. Now, you're looking for elongation, and the SI unit for elongation, or let's call it change in length. Since it's length you're talking about, the unit to be what? Meters, am I right? So you already know your final destination, right? So everything here, you look, everything here, which one is not in meters? You start converting them to meters, because you're looking for elongation, and the final SI unit for elongation is meters. So you cannot use all these values like that, right? You know that you need to convert this one to what? Meters. And if you convert it to meters, it will now be divided by what? 1,000, right? Because you're converting from a smaller unit to a larger unit, right? So if you divide it by 1,000, simple. If you don't know how to divide, you can strike it like this. You strike 1, you carry here. You strike 2, you carry here. You strike 3, you carry here. Your decimal point will be here. So you'll be left with what? 0.2 meters. You see how simple it is to divide? So you not stress yourself. You now look again. What do we have again? What do we have? Okay, we have this 80 millimeters by 80 millimeters. And you need it to be in meters, right? So you now bring it out. 80 over 1000, right? So you cancel here, you carry here. You cancel here, you carry it out here. You cancel again, you carry. You put 0 here. So this is where your decimal point is, right? So it will not be what? 0. What? 0.08 meters. You see how conversion is very important. You need to learn conversion. You see, in the first chapter in physics, it's conversion they're talking about. Conversion prefixes. All these things are prefixes. That's what they call prefix. Millimeter. This M now, let me write it here. 80 millimeters. Take note, this is the magnitude. This is the magnitude. This here is the prefix. And this here is the SI unit. See the difference? This milli now as a prefix simply means 10 raised to the power of minus 3. Am I right? Milli, 10 raised to the power minus 3. Now we know that kilo is 10 raised to the power plus 3, right? Milli is minus 3, kilo is plus 3, right? We know that mega is 10 raised to the power what? Plus 6. And we know that micro, this mu, is what? 10 raised to the power what? Minus 6. Are you seeing? So all these prefixes, you need to know them by heart, because most of the things you do in strength of materials, they'll be using prefix to confuse you. You now see the parameters, they are there. You know what they represent, but you just jump into the formula, which is this now for elongation, and start inputting your values. What you're doing, the syntax is correct, but it's wrong. Because of it did not what? Convert. So you are still losing marks already. You see how you lose marks? You know that the formula you applied is not correct, oh? It's correct, but you did not convert. So if you are supposed to get your 14 marks, you have already lost most of the mark already. But once you do this, you do your conversion, you have gotten like 7, 6 marks. Then you're remaining solving your final answer, you have gotten your complete 14 marks. Move to the next question. So let's proceed. So we've converted this to 0.08. So this will be 0.08 by what? 0.08, right? So now let's call our formula. So if we call our formula for elongation, which is this, we have that elongation or change in length, let me use change in length, is equals to what? Force times original length all over Young modulus times what? Area. So what is our value for force? 400 what? Kilowatt Newton. Now look, another thing you should take note of. This force is in kilonewton, right? So you need to cancel out this kilonewton. You need to look again. Where else can I see kilonewton? This is another place you see kilonewton. So since the two of them are in kilonewton, you don't need to convert any of them, right? Because you know they will cancel out. And you'll be left with only meter, because this is what you're interested in. You get? But if you now rush now and say, okay, this is a prefix, kilonewton. Let me convert every prefix I see. You convert this one to Newton. It will affect your elastic modulus. Because kilonewton cannot cancel out Newton. Are you seeing? So if you're converting this kilonewton, now if you're converting this prefix to Newton, you should also convert this one to Newton. So instead of you to save yourself that stress, that long process, leave it like that. So when you're dividing, Newton will cancel out Newton and you will left with only what? Meters. That's why we will not convert the what? Force. Are you seeing it? Alright, let's proceed. So now our force is what? 400 kilonewton, right? Times our length. Our original length is what? 0.2 what? Meters. You know this is in meters, right? This 400 is in kilonewton. Let me write it so you see it. 400 kilonewton. I want you to see how they are cancelling out. All over this now, this man. Young modulus. 8 point what? 8.56 times what? 10 raised to power what? 8. Right? is in what? Kilonewton per meter, right? Kilonewton per what? Meter. Then times what? The area. 0.08 meter, right? So it's 0.08. Okay, let's just do it here at once. 0.08 times 0.08. Someone should point the calculator. 0.08 times 0.08. See it now, 80 millimeter by 80 millimeter. So area will be what? Area will be equal to what? Eh? One person, please. Zero point 64. Okay, another person. 6.4 times 10 raised to the power what? Minus 3. Another person. So do you know the difference between this and this? Okay, let me know. Yes? Correct. So this one is in standard form, or we call it scientific notation. Standard form or what? Scientific what? Notation. The reason for this being sometimes your answers can be very long. So as a wise man and your paper is not that long, your exam script, you need to leave it in standard form or scientific notation. And your calculator, most times, will give you in what? Scientific notation. Then you that will now know your conversion to convert it to what? Standard form. Who knows how to convert this thing now? Or shall I show you? Now, if you're converting this one now, you count 1, 2, 3. That's why we have 10 raised to the power minus 3. You're moving towards the right. But Adibi, you had something like this now. Okay, you have something like this, 6.4. And you want to get it in this normal form, you move it backwards. 1, 2, 3. You add 0 here, you add 0 here. That's this 2 0 back. I think the way they're converting from one form to the other. So you should know that. So now we have 6.4 times 10 raised to the power 3. Okay. 6.4 times 10 raised to the power what? Minus 3, right? And the sign is what? Meter what? Square. So now, someone should punch and give us our final answer. Elongation. I'll be changing length. What's the final answer? Punch. 400 times 0.2. 8.56 times 10 raised to the power 8 times what? 6.4 times 10 raised to the power minus 3. Someone should punch. Please, I hope you're with your calculator. You need to be with your calculator in engineering. Don't neglect punching calculator. Most people fail in exam because they underrate it. They will be like, it's very easy, I can punch. But you know that this is the best time to start practicing. In exam, you are under pressure. You want to be fast, so you can make mistake. And you now start looking for where to punch this symbol, where to do this, where to do that. You'll be killing your time. So start punching now. And please, carry a calculator that has textbook display so that you'll be faster. You know, in exam, you're looking for time, more time. Textbook display, something like this now. Let me show you. Just help me your calculator. Something like this now. This type of calculator you should get as an engineering student. It will buy you more time. Not that you cannot use any other calculator, but this thing will give you more time and leverage because it's giving you the textbook display. They have other higher calculators than this, but this is the acceptable one. If you're using any other one, you're going to be stressing yourself. It's better you go and borrow from your friend, either your junior colleague or your senior colleague. Borrow it and use. Save yourself the strength. Save yourself the time. So you have time for more what? Questions. Thank you. So let's proceed. What's the final answer? Final answer, final answer. 1 point what? Please, another person should confirm. 10 raised to the power minus what? Minus 5. So what's the symbol? Meters. So now let's just bring out only the symbols, the SI units, out one side and see how they cancel out. Should we do it? So now we have kilo Newton times meter, right? And in the denominator, we have kilonewton meter. times what? Meter square. So now, watch how they cancel out. Watch why we landed with just meter. Are you seeing? Let me explain to you. Now, you have kilonewton over meter here. This now, we cancel this, right? We have 1 meter here, we have 2 here. So this will be left with just 1, right? Then now, let's rewrite this now. Where should I write this thing now? Let's rewrite it here. I want to show you how you get your, what they call, your unit for that change in length. So we've cancelled that. So we left with what? Kilonewton times meter, right? All over kilonewton times meter. So this, we cancel out this. How come? We're supposed to have one more. We're supposed to have one more. So let me check. 0.2 what? Millimeters. Original length, okay. Where? That's this one. This one. Okay, this one. Okay, it's square. Okay, so the square will cancel out square, so we're left with nothing, right? All right, thank you for noticing that. So we're left with nothing here, right? So kilonewton will now cancel out kilonewton, and our final answer will be left in what? Meters. So please understand those SI units and prefixes, how to manipulate. Even without looking at it, as you just read the question and they just say extension, you should know that your answer will end in meters. So everything here will convert. Very simple. Once you have looked at it, you understand it, then you proceed. So let's solve another question. Let's solve another question. Are you done writing? Okay, let's solve another question. Here's that question. Let me look for a complex question. Would I call it complex? Not really complex, but a question that will test us. Okay. Take note, take note, take note, take down. Are you done? Take down this question. Take down this question, please. A steel bar is 1,800 millimeters long. A steel bar is 1,800 millimeters long. Are you there? Each two ends are 80 millimeters long and 60 millimeters and 60 millimeters in diameter. Take note. Each two ends are 80 millimeters and 60 millimeters in diameter. The length of each end is 400 millimeters long. The length of each end is 400 millimeters long. The middle portion of the bar, is 30 millimeters in diameter. The middle portion of the bar is 30 millimeters in diameter. If the bar is subjected to an axial tensile load stress, if the bar is subjected to an axial tensile load stress of 30 kilonewton, find the total extension. Find the total extension if E is equals to, in bracket, if E is equals to 200 giganewton per millimeter square. Per meter square, sorry, not millimeter square. Let me write that one down so you will not get confused. If E, okay, so I said 200 giganewton per meter square. So you know what giga is? What's giga? 10 raised to the power what? 9. What about mega? 10 raised to the power 6. What about kilo? So we can say if we add kilo and mega, we get giga, right? Okay. Let's leave that there now. All right. So what were we given? Please call the values we're given. They say the steel bar is what? 1,800 meters long. Okay, so this question, take note. When you see this type of question, now you start thinking, do you know what they call line idealization? Or how to represent something in forms of a 2D drawing? Line idealization, you draw out what the question looks like. You know, engineering, there are so many things you draw. Like, let's say for instance, in physics now, during my own set, they gave us a question on hydrometer, where they tell you something is deep into hydrometer, the other one is deep into mercury. Which one will have blah, 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 and blah. I don't know if they asked you that question in your own set. So that question was my number one question. I answered that question, 10 marks. So that's the question. Now, this now, from our question, we are given something like, let's draw it here. They say the bar, for a bar, right? They gave us diameter, so we know that the bar is circular, right? First of all. And now, let's say the bar is like this now. And they're telling us that the length of this bar, let's say this is the middle, right? Please, which of you is good in technical drawing here or engineering drawing? If you love technical drawing, raise up your hand. You like it? If you don't like it, raise up your hand. Jesus. And you're in engineering. Ha. Please, start liking it. If you actually later, you can come and meet me. Because why is that? As an engineer, you're a professional. You're not just be working with people that can speak English with you. You work with people that are speaking other languages like Spanish, Latin, French. So how do you communicate with them? Your drawing, very simple. So your drawing should be well detailed so that they can interpret what you are communicating. Even though they cannot hear English, at least they can see, they can understand numbers, and they can know what a shape looks like. If you draw this thing now, if I draw something like this now, without talking, and ask you, what is this thing now? What will you tell me? Eh? A what? Because you say that bacha. Did I hear bacha? Okay, mud house. But it's still a house. You see somewhere that I can seek shelter, right? How do you know that it's somewhere that I can seek shelter? Because of you are seeing windows, you are seeing doors. You see? So someone that is even in Chinese, Haiti, India, if he sees this thing, you understand. This is what they call engineering language of communication. It's not those big grammar you speak. Oh. When you're on the field, it's your drawing that will speak loud for you. Either they will pay you serious money to design. If you know how to use software to design, you earn serious money. AutoCAD. Who knows how to use AutoCAD here? You know how to use AutoCAD? Who else? Anybody? Okay, who has heard about AutoCAD before? You've heard of it. So what is AutoCAD from what you've heard? Just tell me what you understand by AutoCAD. Eh? Designing with system. So AutoCAD is a computer-aided design. So that thing you're drawing manually, your computer is aiding you to draw it faster using your system, right? Using softwares. It's very important. It's not only AutoCAD that is there, but AutoCAD is like the mother of all of them. Because any drawing you're doing, you still bring it back to detail it. And mostly you use AutoCAD. You have Civil 3D, you have Revit, you have ETAP, you have different softwares for different departments. So please learn softwares. Even for data analysis, you have different softwares. Let's come back to this. Our question says diameter, right? 900 meters long. So this is 900 meters long. Is it meters or millimeters? Okay, sorry. 1,800. Right? And they told us that it has 3 different diameters. What's the first diameter? The first diameter. Eh? Okay, let me read this from here. There are 2 ends, 40 millimeters and 30 millimeters diameter. So diameter 1 is what? 80, sorry, God. 80 millimeters D2. 60 what? Millimeters. D3 is what? 30 millimeters, correct. So now, what they say we should find? They say find the total extension, right? So total extension, that's the same thing as elongation. The total one. So our answer will be what in meters, right? But we don't know the answer yet. It's unknown. But our answer will be meters in meters. So all these things now, we'll convert them, right? All right. This one now, we will not convert this one. But this giga now, we can convert it based on, let's see. Now, our tensile stress. What's our tensile stress? 30 kilonewton, right? So that's the load. The tensile, this is what? 30 kilonewton. So now we're looking at the tensile stress, the load, and the Young modulus. So now, are you looking at it? What is the difference? This one is in giga, this one is in kilo. So they cannot cancel out, right? So we either convert this one to giga or convert this one to what? Kilo. So now let's go back to this thing I wrote here. This is giga, right? This is kilo. This is mega. So now, if we want to convert this 200 to what? Kilo. What do we do? 200 what? Giga Newton per meter square. It's simply what? 200 times 10 raised to power 6 times 10 raised to power what? 3 per what? Meter what? Square. Right? So now we know that this is kilo and we want to give our answer in what? Kilo. Right? Let me put the Newton, sorry. So it will now be what? 200 times what? 10 raised to power 6 times what? 10 raised to power 6. This 10 raised to power 3 will now be what? Kilo, right? That's this now. Newton what? Per what? Meter what? Square. Are you seeing how we converted this? Who doesn't understand? Let me recap. Do you understand what I just did there? Alright, very good. So we have converted this one now. These ones now, we divide them by 1,000. So we have 0. What? 08. We have 0.08 meters. We have 0. What? 06 what? Meters. We have what? 0. What? 03 what? Meters. You know I'm converting it? I'm dividing it by what? 1,000. So we have gotten all of them in what? Meters, and we have made this one to be kilometer, kilonewton, kilonewton. So now, in case you are cancelling out, we will leave our answer in what? Meters, right? So now we can proceed to the next phase of the question. Now, you have a question? All right. So now they say the length of each end is what? 400. So now we'll cut this thing into two. They say 2 ends. Is it one end or two ends? Okay, each end is 200 meters long. So now this will be what? Let's draw it down. Please, I hope you're understanding my drawing. 200 what? Okay, 400. Is it millimeters or meters? Okay, 400 millimeters. So let's convert it to meters to be what? It will be 0. What? 0.4. Let's use 0.4 at once. 0.4 what? Meters, right? Over this one, if we convert 1800 millimeters, we will get what? 1.8 meter, right? And now this one too will be what? 0.4 meters. So now take note, the total length of the bar from here to here is what? 1.8 meters, right? This is 0.4, this is 0.4. So what will be the middle one? You add these two and subtract it by the total length, right? So what do we have? 1 meter. So the center one will be what? 1 meter. So we have gotten the length of the what? Bar. Now they say that this bar, the first diameter is what? 80 millimeters, right? So now let's reduce the second one now. Since the first one is different from the second one, we are redrawing our shape. They say the first one is what? 80. The diameter is what? 80. The next one, they say something like 15. So it should be smaller, right? This is our D3. That's the center one. 0.3, right? Then the last one, they say something like 0.06. So it should be smaller than this one, but bigger than this one. So it will be something like this. This is how our diagram will be. I want you to just picture it out. So this one now, the diameter here is what? 0.08 meter. Here is 0.03 meters, and here is what? 0.06 meters. Are you seeing it? So the material is not stable. It's going up and down. Then now the length too, now we have seen the length. So now what do they say we should find? Elongation. And now they say that the force acting on it is a tensile force. So tensile force drags the body out. I'll explain why it's like that. Let me show you why. So now we have two types of stress. Take note. We have two types of what? Stress, right? We have the tensile stress. And we have the what? Compressive what? Stress. For the tensile stress, now let's say this is a body, right? And we drag this body. As we are dragging this body, as it's expanding, the length is increasing. But the thickness is what? Reducing. Right? So this is the concept of what? Tensile stress. As you're dragging it, the length is increasing, but the thickness is reducing. While for compressive stress, it's the opposite. Now, this is the body, right? This is the body. As you're compressing it, as you're pressing it, the what? The length is reducing, but the thickness is what? Increasing. Let's just say, for instance, you put water inside container, like water bottle. If you are squeezing it, the size of the diameter of the bottle is reducing, right? and the water is increasing in the bottle. So that's something of compression. You get? Now let's go to mishai, bread. When you go to the mishai guy, your bread is full, right? When you finish, you now pour oil and start pressing it. Because they say press and press and. As it's pressing it down, right? It's just assuming that something is dragging it from the side, making the bread now to be sharp. So the egg will be here like this now. Now the bread now is what? As it's dragging it, the bread is shrinking. It's shrinking. So you'll not be asking the man, okay, you cut some of my bread, give another person. Abi, the bread still remain. So this is how it is. As you're pressing it, the length is increasing, but the bread is what? Reducing. But for the water bottle, let me draw it. This is the water, right? You now exert force on it, compression force. As you're pressing it, the water is increasing. The water will now be somewhere here, right? But the bottle now will now shrink. It will now squeeze. Are you seeing it? So this is the concept of the compression. Why this is the concept of the what? Tensile, this is. So now, this one now, as they are dragging it, the middle is reducing. You know, the original size was like this. So because they are dragging it now, the center is now reducing. That's why the center is reducing like this. Because of that tensile force. So the question itself is also a logical question. So now how many, okay, 30 kilonewton, right? 30 kilonewton is applied here. The same force, 30 kilonewton is applied here. So now let's start solving. Now we're looking for elongation, right? And this is our formula for elongation, am I right? Okay. Oh, they've even written solution for us. All right, let's proceed with this. So this is our solution, right? But now, take note. Since we have different length, right? The first length is 0.4, the second one is 0.4, this one is 1.0, yes, 1.0. We have different lengths, and we have different diameter too. Are you seeing it? So we have different area. Why? We know that area is equals to what? Pi d square over what? 4. And we have three different diameters. Take note. We have the first diameter, we have the second diameter, we have the third diameter. So from this equation, we told us to find not just elongation or change in length. They said we should find the total elongation. Look at it. CE, that's the total, right? And if we are saying total, that means we have elongation in this first body, we have elongation in the second body, and we have elongation in the third body. Then we add the three of them together to get the total, right? So now we know that our total elongation will now be what? Elongation in the first one plus elongation in the second one plus elongation in the what? Third one. Am I right? Hope you're following. And we know that elongation is what? E is equals to what? F times L all over E times A. So now, for the first one, E1, E1, so our total elongation, E1 will be what? Now we'll put this FLEA. But now F is constant. It's the same force that is acting here and here. So it will not change. Now, for E1, the first length is this length. So we'll call it L1, right? So it will now be F times L1 all over E. That's the Young modulus. The Young modulus is also constant. Take note of the constant ones that are not changing. The Young modulus is constant. It's just one Young modulus. The force is just one force. But the diameters, they are 3. And the length, they are also different, right? So now, E1 will be what? FL1 over EA1, right? Plus FL2 over what? EA what? 2, right? Plus FL3 over what? EA3. If you're lost, please let me know. Let me recap. Are you following? You're following? All right. This represents E1. This represents E2. This represents E3. Now, looking at all this, you know you can factor out. You can factor out, right? So if we factor out what is common between the three of them, we know that F over E is the same here, F over E is the same here, F over E is the same here. It's not changing. So now we'll bring it out. Factoring simply means, if I say 3 is a factor of 9, simply means 3 can be used to divide 9, right? So now, if 3 can be used to divide 9, to get 3, right? So if you also want to get this 9, if you use 3 times 3, you also get 9, right? So they tell you now you should factorize 9 times 3, or you should factorize, let's use plus. 9 plus 3, you now have what? 3 into what? 3 plus 1, right? Because 3 times 1, 3 times 3 will be what? 9, and 3 times 1 will be what? 3. So that's what we are trying to do now. We are factoring out this. So it will now be what? We bring out F over E. We now have what? L1 over what? A1 plus what? L2 over what? A2 plus what? L3 over what? A3. So this is how it will look like. So next up, we'll now use, since we already know L1, L2, L3 as 0.4, 1.0 and 0.4. Now we don't know A1, A2, A3. Now for this now, the formula is pi d square over 4. But now this is changing. So we'll have D1. We'll have another one again. Pi D2 square over 4. We also have another one again. Pi D3 square over what? 4. To get A1, A2, and A3, right? So now, someone should punch for us. For A1, pi D1 square over 4. What will we get as A1? Pi is a constant, right? 3.14, right? So please punch. There's also pi in that calculator. Shift something, you see pi on your calculator. You are seeing pi down, right? You have seen it, right? Punch. So now D is what? D is what? 0. What? 08 square over 4. So what's our answer? Be punching, sharp. So now D2 is what? 0.03. This is the diameter, right? Are you looking at it? 0.03. So it will now be what? 0.03 all square over 4. So what's the first answer? 5 point what? 5.03 times 10 raised to the power what? 10 raised to the power what? Minus 3 what? Area is in what? Meter square. So now, the next one, what's the answer for the next one? Be punching that one. And the third area will be what? Pi d3 square over 4, which will be what? Pi into, our d3 is what? 0.06. 0.06 square over 4, which is equals to what? Please help me punch. Which of them? 2 point what? 83 times what? In what? Meter square, because it's what? Area. Then the third one. Punch. Eh? 1.7.07 times 10 raised to the power what? Minus what? Why are we having minus 4 in this one? Punch it again. Punch it again. Punch that last one again. Why are we having minus 4 in the last one? When others are having minus 3. Punch it well. It's minus 4. And the other one is minus 3, you're sure? Alright, let's proceed. So now, we've gotten our A1, A2, and A3. So we can substitute it here, right? We also have our force, we have our young modulus, and we have L1, L2, L3. So we have gotten everything we need, right? So it's just to substitute and get our what? Final answer, which is the total elongation, right? So let's do that. I can clean these values now. You give them to me. Please take note. This is our new young modulus. This is what you give to me for the young modulus. We converted it to kilonewton. All right, let's go. All right, proceeding. We have that total elongation is equals to what? Force over young modulus. What's our value for force? 30 what? 30 kilonewton over what? What's our value for young modulus? 200 what? Times 10 raised to the power what? 6. All right, into, now, look, watch closely. What's our L1? 0.4, right? This 7.07 is for which one? It's for 0.3. Because I was wondering the values, why are they changing? All right, thank you for noticing that. So this will be what? 7 point. You say this will be what? 7.0, right? 7.07. Why this will be what? 2 point what? 83, right? So this will be what? Minus 3. And this will be what? Minus what? 4. All right, thank God you noticed it fast before we started solving. So let's go back to this. So now we are simply substituting in our values. L1, L2, L3 is simply what? 0.4, 1.0, and 0.4. A1, call A1 for me. L1 over A1. 0.4 over what? What's A1? 5.03 times 10 raised to the power what? Minus 3 plus 1.0 over what? 7.07 times 10 raised to the power what? Minus 4, right? All right. Plus 0.4, that's L3, right? L3, that's this one. 0.4 times the area, that's A3. See the formula we are getting here from L1 over A1, L2 over L2, L3 over A3. L3 now, 2.83 times 10 raised to the power minus 3, right? 2.83 times 10 raised to the power minus 3. Someone should please punch and give us the answer. Give us this one first, then give us the one inside the bracket next. So ET will be what? 30 over this first. Give us this one. 30 over this. 100 and, okay. Can you give us in standard form? 1 point what? Times 10 raised to the power what? 5, right? Is it 150,000? Let's confirm that. Okay. 1, 2, 3, 4, 5. Okay, correct. Okay, so what's inside the bracket? What's inside the bracket? What's inside the bracket? Add this one to this one to this one. Add these three. As I say, you should use scientific calculator so you'll be fast. So let us know what our answer is. This plus this plus this. Let us know, let us know. It's already our break. So people are the ones holding us. Let us know. 1,000 what? 1.5 times 10 raised to the power what? 7. For this one. Okay, another person, please confirm. Another person, please confirm this one, this over this. Confirm that one. Okay, minus 7. Minus 7, right? Please punch because we need the correct answer, please. Punch this one, punch this one. That's why you need to start punching now so you can start making the mistake now. So inside exam, you won't make that mistake. So start punching, punch. Well, I want everybody to punch, please. If you're with your calculator, punch. If you're not with your calculator, download scientific calculator on your phone. Use your phone and punch. So when you have money, you can buy calculator. Please punch, punch, punch. Your calculator, where's your calculator? Download it on your phone. You can download scientific calculator on your phone. Download scientific calculator on your phone so you can punch. That one is the same thing with the one in your hand there. Punch, punch. Chief, you're not punching. 1,000. You're getting 41. We can get 10 different answers here if everybody punch. You can even get up to 20. So punch, punch. I want everybody to punch. We'll collect the majority answer. Majority. So what do we have? What did you say you have? What did you say you have? 1,000. What did you have? Point what? 0.32. Next person, what do you have? 1,635. Point what? 29. Any other person? Punch, punch, punch. We can get more answers. So I will know the one that is correct. You're getting what? You're getting 1493 point what? 0.95. You see why? You see what I'm getting? Continue punching. Sure, you know what you are adding? You are adding this plus this plus this. Punch, oh, you think it's easy until you punch it by yourself. That's how you know that what you are punching is not just to punch calculator. Punch, punch. Big man with calculator, you're not saying anything. Which one did the person say? The second one. So the second one has 2, right? If you are going with the second one, let us know. Who else is having second one? You are going with the first one. We know now. We want to know how many people have this. So we'll collect the majority. Eh? Hmm. Hmm. Okay, times this one. It's wrong. Okay. Okay. So which one did you give me? Which one did you give me? This one. You gave me the second one. So everybody is getting the second one as the correct answer. Who said no? Not everything, no, just these 3. Or should I punch? I should punch. But if people are the ones learning, I the one that will write the exam. If I punch, I'm not doing any good. You got what? 2.3. Wow, I like the answer. 2.3. What did you punch? Times 10 raised to the power what? Minus 10. Minus 4. Beautiful, beautiful. All right. Who else? Who else? See how hard it is to punch a calculator. See what you are adding, this, and this. And we'll go for our break. So people should allow us to go for our break now. Please, people should be fast about it. When you punch this one, they will not times it by this one. Punch, punch, punch. Okay, you already done the answer. You are getting 8.56. Jeez, that's nice. That's nice. 8 point what? 8.56 times what? Minus what? 10. 3. Wow, we have gotten 5 answers. Keep punching, keep punching. That's how you know that to punch calculator is not easy. And in exam hall, you see people seriously calculating, you're copying from them. You think what they're punching is correct. You know that they're punching nonsense. See the problem. I see the problem. I copied everything. The guy good, the guy good. So punch the calculator is the problem now. I have punch, let's see. You got 1,000? Alright. So that's what I also got. 1,635.29. Please, if you got anything apart from this, let me know. Pass this thing now. Everybody, one by one. Look at how they're punching calculator. Look at how you should put your this thing. Pass it. Don't press anything. No. When you look at it, pass to the next person. We are on break. The another person should punch. First of all, call that thing on the calculator. Call it for me. This second one is the correct one. This is the correct one. 1635.29. So someone should times it by this one. Let's get our final answer. Then pass the calculator around. They will not steal it. Don't be afraid. If they return back the calculator, you should be thankful. Your name is on your calculator now. 2 point what? Let me see. So please punch this. This is 1.5 times 10 to the power minus 7 times this one. Punch, punch. So you will know where you're making mistake from. Please punch, oh. Punch. Punching will save you a lot in the exam hall. Punch so we can go on break. We've taken like 9 minutes inside our break. It's already 12:30. Eh? You're getting minus 3, you're getting minus 4. Okay, let's get the answers. What and what do we have? Wait. Just be giving me your answers. So the first person, what did the first person get? What did he get? 2 point what? 4 times what? Minus 4. Big man, what did you get? Another person was saying another answer there. What did you get? The third person, what did you get? 2.35. Check now, check the something there. You got the first one. So the first one has 2 persons, okay? 3 persons. 4 persons. Okay, one is 2.5. Wow, that's beautiful. 2 point what? 2.5 times 10 raised to the power. Remember, this is what you are punching, no? Next person. Okay, you have changed your to minus 3. Your is 2.5. Wait. I hear 2 point what? 2.53. 2.53 times 10 raised to the power what? 8. I do not to do. Eh? Just raise your calculator up. Then I'll ask. Which one did you choose? So I will ban that calculator. Because I don't know whether it's your calculator that's giving you the wrong answer or you're the one pointing the wrong thing. It's the first answer. You are very sure. That's what you have now. That's your own answer now. So what about these other people? You see the problem we have? Very simple things, but because of pressure, you make mistake. Please, you are done for the first section. You can go for your break. Let me just punch it and give you the real answer. We are done with the first section. Well, let me give you the real answer. 1.5 times 10 raised to the power what? Minus 7 times 1635.29. So the correct answer is the first one. The first one is the correct answer. So please, 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 this is the correct answer. And you say you wanted to change your own. So you got it. Okay, okay, well, minus 3 before. Okay, correct. So this is the correct answer. And the unit is what? 2 point what? 45 times what? 10 raised to the power what? Minus 4 what? Meters. In a tensile test run, the yield load is 260 kilonewton. The ultimate stress is 140,900 kilonewton per meter square, and the rupture load is 210 kilonewton, and the rupture load is 210 kilonewton. Are you following? Where are you? Where did you stop? Eh? Okay, ultimate stress is 140,900 kilonewton per meter square. That's 140,900 kilonewton per meter square. Are you there? All right. And the rupture load is 210 kilonewton. If the diameter of the circular bar is 80 millimeters, if the diameter of the circular bar is 80 millimeters and the neck diameter, the neck, N-E-C-K, neck, and the neck diameter is 30 millimeters, estimate the maximum load. Estimate 1, the maximum load. Estimate I, the maximum load. II, the tensile yield stress. II, the tensile yield stress. III, the rupture stress. The rupture stress. IV, the percentage reduction in area. IV, the percentage reduction in area. So let's proceed. So please give me what we have there. Given so the yield load. Okay. Yield load 260 kilonewton, right? You know, stress can be written as a symbol sigma. So sigma u as what? Ultimate stress, right? Equals to what? 140,900 kilowatt newton per meter square, because it's what? It's a stress. That's first of all here. Okay. The rupture load the rupture load 210 kilonewton. Okay. The diameter of the circular bar. So the D1 circular bar, okay, let's say DCB, that diameter of circular bar is what? 80 what? Millimeters. The next one, the second diameter, the neck diameter, right? That is D neck, is what? 30 what? Millimeters. What else? All right, so we say we should find what? The max load. So we don't know the maximum load. We don't know the tensile yield stress. Since it's tensile stress, right? So let's use sigma T. We don't know the tensile yield stress. We don't know the rupture stress. Sigma R. And what else? So we don't know the percentage reduction. So we are looking for 4 things here, right? All right, let's proceed. So now, looking at the question, they are trying to confuse us by giving us two different diameters. And now, there's something that, let me just draw something now. So now, let's say this is how the material was, in quotes. They said dragging it. So now this is like the neck. This is they call like this thing is small like this. This is the neck. If you drag it more than like this, it's going to what? Fracture, right? So they gave us the stress, different stresses. Now, they told us that we should first of all find the stress that will act on this body. The first stress, that's the what? Maximum load. Right? We know that they gave us ultimate stress. And ultimate stress, sigma U, is equals to force over area, right? And now, since it's the ultimate, that's the total. So the force that will act on it will be the maximum load, right? So that is this one, maximum load. So let's call it maximum load. And we don't know that. And we have the area, right? Now for the area, they gave us the area of the circular bar, because it's a circular bar. But this is a two-dimensional representation. So for the circular bar, they gave us that the area, the diameter of the area, you know, area is equals to what? Pi d what? Square over 4. And they gave us this diameter as what? 80 millimeters. So now, look at our ultimate stress. It's in meters, right? So what do? We'll convert it. So how do we convert? We'll divide it by what? 1,000. So if we do 80 over 1,000, what do we have? 0.08, right? Meters. All right. So now we'll have that area will be equals to what? Pi, please punch your calculator, into 0.08 all square all over what? 4, right? Please punch and give us our area. While you're punching, look up. One person should punch, the rest should look up. Now, we are looking for maximum load, right? And we have ultimate load. And ultimate stress as this. We are about to get our area, right? So remaining the maximum load. So we'll make maximum load here, subject of the formula, right? So if we want to make it subject of the formula, what do? We cross multiply, right? Are you sure? We will not throw it away, we just cross multiply. Okay. So you say we should cross multiply. So let's just cross multiply. So we have maximum load to be equals to what? Ultimate ultimate stress times what? Area. So that's for the first one. So now please punch for the area. Let's get 5 point what? Okay. We are having different answers again. We just call the full value first. 5.0. Did you round up? Have you rounded down? Eh. You want me to start punching calculator? Okay, you say 5.06, 5.03. Yours is 5.0024 times 10 raised to power what? All of you are getting minus 3. Okay, fine. Whether we have 0.2, whether we have 0.3, because it's after the decimal point, the value will be very small, right? So it can be said to be negligible. So let's just use 0.3. 0.3 times what? 10 raised to the power of what? Minus what? 3 what? Meters squared. Because it's what? Area we're talking about. So now we've gotten our area and we have our ultimate stress. So now we simply what? Impute the values to get the what? Maximum load. Doing that, we have that we proceed with that. We have maximum load is equals to what? Ultimate stress times area. And we have our ultimate stress to be what? Please call the value 14 what? 140 what? 900 times what? 5 point what? Area 5 point what? 5.03 times 10 raised to the power what? Minus 3. So what will be our final answer for what? Maximum load. Seven what? 008 point what? You're having 0.24. You're having point what? Please. It's now I know what I'm saying. If I use this calculator, please don't use it. Use your phone. Please. Download that. Don't use it. This calculator will give you wrong answer. This is what I want to be seeing. Point what? 73 point what? Approximately. What did you get? 72. Be giving me in two decimal places. That's 73. 73. All right, please in two decimal places. 0.73. Okay. 0.7 what? 3. Now this is load, right? So it will be in what? Kilowatt Newton. Do you know why it's in kilonewton? Because this one now is in kilonewton per what? Meter square. And area is in what? Meter square, right? So this will cancel this. And our final answer for the load will be in what? Kilonewton. So let's proceed. So now we are done with this, right? So the next thing we are looking for is the tensile stress, right? So now for the tensile stress, we'll ask ourselves, what's the formula for stress? Force over area, right? And now, this is tensile stress. That means we need to have tensile load, or tensile force. Were we given that? Okay, we are giving yield load. What did they tell us to find? Is it the tensile stress or the yield stress? Tensile yield stress. Okay, so we can use the yield load, right? So now we'll have what? Yield load Yield load. What do we use as our load that last time? Okay, we just wrote it as, okay. So that's yield load, that's Y load, over the area. We have already gotten our area, so it's the same area. Since you are working with this body, this is the same body we are still working on. So the area did not change. That's why we are using the same area. Am I right? All right. So now what do we have as our yield load? This is our yield load. It was given in the question there. 260 what? Kilonewton over the area. That's 5.03, right? All right. 5 point. Someone should punch, please. Times 10 raised. Okay, another person should confirm, please. Another person should confirm. It says 51 what? Point 86, right? So now this is what? Stress, right? So it's going to be in what? Newton per what? Meter square, right? Please, another person should confirm this answer. Is it correct? It's correct, right? All right, let's proceed. So we have gotten the second one, right? So next up, we are looking for the what? Rupture stress, right? Okay. So when we giving rupture load, we are giving rupture load, right? Okay, so we'll do the same thing. So rupture load, so rupture stress will be equal to what? Rupture load. What do we use to represent it that time? Okay, let's use arrow. Rupture load over what? The area. Now, what is our rupture load? 210 what? Kilonewton over the area. What's our area there? This is our rupture load, right? And this is our area, 5.03, right? So it will be what? 5.03 times 10 raised to the power what? Minus 3. Please be punching. So our rupture stress will be what? Please be punching, be punching. People are talking like my AI. 41,700 and what? Point what? Kilonewton what? Per meter square. Please, oh, we corrected this one to what? Kilonewton. Take notes. All right, so we'll proceed to the last one. Percentage reduction in what? In length. In area. Thank you. It's area I was expecting you to hear. So now, this is our first area. That's this one now. Now, the thing now reduced. Because of this one has gotten slim. So this space now is empty. So the area will not be the same, right? The shape has changed. So now they're asking us, what is the reduction that happened? Please understand the question. And when you talk about percentage, it's just like a ratio, right? Now, percentage reduction, the formula for that will look like this. Percentage reduction will be something like this. The area that we'll find, that's the neck area. We'll use this neck diameter to find another area because we need two areas. The neck area minus the original area. That's the neck area, the area of this shape, minus this other shape, right? There are two different shapes. Take notes. Over the original area, right? Then times 100. So, okay. The diameter of circular bar. That's what we used to get our first area. Remember, this was the diameter of circular bar. We used to get our first area. That's this one. So now we'll use the second diameter to get our next area. That is the neck area. So now let's proceed. Let's look for our next area here. So the neck area will be equal to what? Pi d. The d is what? D neck. D neck square over what? 4. So please, I'm looking for space. So should I clean this place? Let me clean here. Okay, see it here. Have you finished writing it? Okay. So the neck area is pi d neck square over 4. So the neck area, that's AN, will be equal to what? Pi. Convert this 30 millimeter to beta will be what? 0. What? 030. How do we get it? We divided 30 by what? 1000, right? Over what? 4. So please punch and give me the answer. Punch and give me the answer. Please, another person confirm. 7 point what? And the symbol for area is what? Meter what? Square. So now we've gotten our what? Neck area. We have our original area. So we'll find the what? Percentage what? Reduction. So now let's impute from this thing. We'll impute and get our percentage as what? Neck area is this. 7.065 times 10 raised to power minus 4 minus the original area, which is this 5.03 times 10 raised to power what? Minus 3 over the original area, which is this. That's the same thing as that A. 5.03, please be punching, times 10 raised to power minus 3 times what? 100. All right, please punch and give me your final answer. Please punch and give me your final answer. Please punch and give me your final answer. Yes, times the 100. Negative what? Minus what? 85 point what? 95. Please, another person confirm. Did you approximate? It's 95, right? It's 95. So, do you know why we have a negative here? Because it's a reduction. You tell us, you say something. Okay, that's another reason. So, that's our answer. Yes, we are done with the question. Why do we not use diameter of circular bar? I don't understand your question. Yes. Yes. Okay. Now, if we watch the question, the first 3 things they told us to find was based on this bar. And at that point, they did not tell us anything about reduction. So everything you are solving is based on this shape, this bar. Because in the last question, we now knew that something like reduction happened. You get? So now, since we know that reduction happened, that means the shape has changed, right? That's why we will now bring the new area. They will now compare the both of them to know the amount of change that happened, the degree of change. So it reduced and became 85% minus 85%. So if you minus 100% by this 85%, you know the amount that is there. 14 point something left, right? You see? So that's the percentage of reduction. So you do 100 minus this. 100 minus this to get, punch it please, let me get. 14 point what? 14.05. So it's now be 100 minus 85.95, which will give us what? 14 point what? 05%. So this is the percentage reduction that happened. All right. Yes, yes. Okay. Now I'm watching what this boy is doing. All right. See, let me tell you now. I told you now that the shape changed. As you're stretching it, it's the middle is becoming smaller because you want to fracture. So this neck now you're already seeing it. That's why I drew it. So what you're saying is the same thing with the drawing. You get. So if you can look at the drawing, to now translate to what you're saying. So it's the same thing. You get. All right. Let's move to what thermal stresses and what thermal strain. What do you understand by the word thermal, please? Heat. I know that River State of late has been very hot, right? Why is that? Why do you think the place is very hot? Because of March. This one say because someone enter hellfire. Okay, the economy is affecting the weather. All right. So it will reach everybody. No, don't worry. So it's not because of greenhouse gases, I mean. It's not because of the ozone layer is being depleted. It's because of Nigeria economy. Okay. So I'll be introducing thermal stress and strain. Imagine if this class was very, very, very hot. What will happen? And people are inside. What will happen? Eh? You say you have heat rashes. You start reacting. To be what? You burn. Wow. Some people will sweat. Some people will not even sweat. I'm telling you, some people don't need to sweat too. Some will faint, exactly. But it will not be a boy, sha. It will be a girl. But some boys will still faint too. Yes. Then everybody will be sweating. The place will be uncomfortable. Some people might even expand self. It's possible now. Okay, let's go. Thermal stress and thermal strain. Have you heard of the word linear expansivity before? So you've heard of the word linear expansivity before. So where did you hear it? Is it in school here or your secondary school? So what is linear expansivity? Who knows the definition? So take down. Okay, what does answer the question? All right, take down. Eh? And we have already finished. I'm just like, this is not, this is where the answer stopped to. But I'm just showing you something. Like, if you ask you another question, like how many percent reduced, like how many percent was lost, you now do 100 minus this. You get. But this is where your answer will stop. This is where your stop will stop. Nothing concerning you with this one. Please. It's just for, we are engineers, so we are thinking outside the box. You get. So now, thermal linear expansivity, take note, please, take note. Does anybody know the definition here? All right, linear expansivity is the what? Change in length. Is the change in length per unit length per unit change in what? Temperature. Mathematically, linear expansivity, okay, let me repeat the definition. Linear expansivity can be defined as the change in length per unit change in what? Temperature. Mathematically, it is written as, this is alpha, right? Alpha is equals to what? Change in length. This sign represents change in length all over what? Length per unit what? Change in what? Temperature. So this is what linear expansivity is. Now, we want to make change in length subject of the formula. What do? Cross multiply, right? So we have what? Change in length will be equals to what? Alpha times what? Length times what? Change in what? Temperature. You know, this can also be written as what? L2 minus L1 all over L into T2 minus T1, right? We have smart students in the house. Clap for yourself. People are doing very well. At this stage, right? Okay, I knew it, but it's not that they taught me. I learned it by myself. It's not that they taught us in school. And I'm sure most of you remember this thing from secondary school. So your brain is very hot. This is not what they taught you in year one, Abi. It's from secondary school you're remembering this thing, right? So clap for yourself again. It's not easy. It's not easy. So now, let's talk about thermal strain. Thermal strain. For thermal strain, you know, strain, we say strain, the Greek symbol for strain is what? Epsilon, right? So now, if we say thermal strain, let's use epsilon T, right? For thermal strain. Are you following? All right. And we say that strain is what? Strain is equal to what? Change in length over the original length, right? So write it down. Change in what? Length over what? Original length. And we know that change in length can also be written as alpha length times change in temperature, right? So we simply what? Substitute. So we have that thermal strain. Let me write it here so you remember. Thermal strain. Are you following? So we have that thermal strain, epsilon T, will be equals to what? Change in length, which is what? Alpha L change in T. Alpha L change in T all over L, right? So now what is common? L is common in the numerator and the denominator, am I right? So we'll cancel out and we'll be left with what? Epsilon T, that's thermal stress, thermal strain, sorry, will be what? Alpha what? Change in what? T. Do you understand how we got there? If you don't understand, please let me know so I can recap. Oh, come on. All right. So now let's look at what? Thermal strain. Thermal what? Strain. Stress. Sorry, we are talking thermal strain. Thermal stress. Now we know that thermal stress. First of all, stress is written as what? Sigma, right? So thermal stress is sigma T, right? And we know the relationship between Young modulus and stress and strain, right? We know that Young modulus E is equal to what? Stress over strain, right?
Yes.
That's sigma T, thermal stress, over epsilon T, thermal strain, right? So now, from this now, right, we want to get thermal stress. So what? Cross multiply, right? So it's not be your modulus times what? Thermal strain, right? So thermal stress is not be what? Your modulus E times what? Epsilon what? T. Are you seeing it? So now we know that epsilon T is equal to alpha change in T, right? So we simply what? Substitute. We now have that thermal stress is equal to what? Log modulus E times alpha change in what? T. Please stay close. So that's the relationship between the three of them. That's how you get your thermal stress and what? Thermal what? Strain. So let's solve an example. Then we'll call it a day. The last example before we call it a what? Day. What the time? We have 14 minutes more. Okay, let's solve the last example fast. Are you done writing? Yes. Alright, take down this question. Take down this question. A bar of mild steel, a bar of mild steel, mild, M-I-L-D, mild. A bar of mild steel of diameter 170 millimeter is placed inside a hollow aluminium. A bar of mild steel of diameter 170 millimeter is placed inside a hollow aluminium cylinder of internal diameter 170 millimeter and external diameter, of 220 millimeters. I repeat, a bar of mild steel of diameter 170 millimeter is placed inside a hollow aluminium cylinder of internal diameter 170 millimeter and external diameter 220 millimeter, both bar and cylinder have equal length. Full stop. The resulting composite bar is subjected to an axial. The resulting composite bar is subjected to an axial compressive load. The resulting composite bar is subjected to an axial compressive load of 1,900 kilonewton if the bar and the cylinder contract by equal amount. That's contract, that they reduce by equal amount. Contract. Let me spell it on the board. Contract. Contract by equal amount. Are you there?
Yes.
If they contract by equal amount, A, calculate the stress in each. Calculate the stress in each. B, the temperature of the compressed composite bar is then reduced by 120 degrees Celsius, is then reduced by 120 degrees Celsius, but no change in length is allowed. But no change in length is allowed. But no change in length is what? Allowed. But no change in length is allowed. Compute the final stress in the bar and in the cylinder. Compute the final stress in the bar and in the what? Cylinder. Are you there?
Yes, sir.
Alright, did you get the question?
Yes.
Okay, let's solve. I have to leave that place, I will have space. So take this down. This was also given the question. This table. It's part of the question. Take this down. The young modulus of steel was given as
final stress in the bar and in the cylinder.
young modulus of aluminium Who is that? This is the volume of your sum.
Thank you very much.
The linear expansivity of steel is what? 0.000012 degrees Celsius. And the linear expansivity of what? Aluminium is what? 0.00005 degrees Celsius. All right, so this is what they gave us in the question. All right, you can ask your question.
Will we convert to kilometers per meter or something like that?
You solve like that. You want to watch it.
Why?
But these ones are like constant.
Okay.
You get?
Yes.
They are constant. So you want to watch it. So depending on what they give us as read the question now, if you check the question, did they give us diameter?
Yeah.
You give us diameter, right? And the diameter was also in what? Millimeters, right?
Yeah.
And the other is in millimeters, so you're not converting that one. As I say, you must look at the constant, then work with the constant. Then anyone check is there any force in the question? Check if there's any force.
Yes.
There's force in the question. Is it in kilonewton?
Yes.
So we are not converting anything, we just solve direct.
So now my question is, so assuming the diameter was in meters, we have to
You convert to millimeters, yes. If it was in meters, the diameter was in meters, you convert it to what? millimeters, so I should follow suit with the constant that was given for steel and what? Aluminium. So please take note of this formula because I'll be asking for them when we are solving this question. These are our last questions, so please bear with me before we go. Alright, I can clean this part soon. So now, let me explain this question. They told us that there's a cylinder. Cylinder is circular, right? Let's say this is our cylinder. And they said a steel is placed inside this cylinder. And they told us from the question that the diameter of steel is what?
170 millimeters.
That's what? 170, right?
Yes.
What about the diameter of the cylinder?
170 millimeters.
That's the internal diameter of cylinder. So let's write diameter reference solution. So diameter of steel, we're not converting to liquid, is what? 170 millimeters. And we have that diameter that's the internal diameter of the cylinder is what? Also 170, right?
Yes.
Because this one is entering inside. So if the diameter of this one is 170, the whole here is also 170. So you can fit it and close it completely, right? So the external diameter, what they give us as the external diameter? 220. See, I'm coming down to write all these giving because these are marks. Don't skip them. Don't skip them in your exam. Please, I'm begging you. Don't throw away your marks. Diameter, but you have to be fast in writing. External. Cylinder. So what? 220, right?
Yes.
220 what? Millimeter. So what else? That's all, right? So now the first thing they say we should find. What they say we should find in the question? Read the question. The stress in each. We know that stress in each. I mean, we will find stress in the steel and stress in the cylinder. Right?
Yes.
Alright. But we know that from our stress formula, stress is equal to force over area, right?
Yes.
We know stress is equal to what? Force over what? Area. Now, the area of the steel is different from the area of the cylinder. So you are aware?
Yes.
The cylinder is everything here, while the steel is just this one. So their shapes are different, their sizes are different. But before we get to the area, what was our force given?
1,900 kilometers.
So our force, you know the force is acting on both of them, so it's constant, it's not changing. So let's write it here. Force is what? Equals to what? 1,900 a question. Are we converting the force?
No.
If no, why?
Because you're already given this constant.
Because it's tallying with the constant Young motion. So we will not convert the force. Similarly with the word diameter, we will not convert it because what? Millimeter, 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 millimeter. So we can proceed. Now, this is the formula that we know for stress. And they say we should solve for each of them. So now, since we have two different shapes, we will find area for steel, we will now find area for the cylinder. Then we will now impute it in this formula to get the area of steel, to get the stress in steel, and to get the stress in cylinder. So you can see how our process will look like, right? You can visualize it. So let's go. So now, area of steel equals to what? Pi diameter of what? Steel square over what? 4, right? So put in values and punch your calculator, give me the final answer. Diameter of steel is what? 170. We're not converting, so just write it down. 170 all square over what? 4. Please, what is your final answer for the area of steel? Please punch your calculator, give me the final answer. Say what?
698.
So the area of steel is what? 22,600
698.
and what?
98.
98 is what?
0.01.
For 0 and what do you need? Millimeter square. So we are working for steel. We do for what? Cylinder, right? So area of cylinder please take note of the cylinder now. You know the cylinder is a hollow cylinder. There's hole inside. So if we calculate the total area using the big diameter, we have to subtract that hole. We have to do that hole. So we minus it by that diameter of the hole. Check, you understand? You can visualize what I'm saying?
Yes.
Alright, so the area of cylinder will now be equal to what? I D external, that's the external cylinder, the bigger one, right?
Yes.
Minus what? D what? Internal, right? All square over what? 4. You know why we got this, right? Please don't be confused. If you don't know, let me know so I will recap. Pi D external, that's this external body from here to here, minus D internal, the hole inside, we are moving it because there's a space inside, over 4 to get the area. So now, if we input our values, what will we have? What are we going to get?
1963.49.
So what was pi, what's the big diameter? 200 and what? 220 minus what? 170 all square, all over 4. Please punch and give me your answer for area of cylinder.
1,962.5.
Please someone confirm the answer. Yes.
Yes.
1,963.5.
963.
63 or 62? Majority guys the vote. 62, raise up your hand. 1, 2, 3, 4. 63, raise up your hand. It's a tie. So the veto power. 63. 63, 62, 66. Give me calculator, let me punch. So if I also got You know why this is happening like this? Some people use 3.14, some people just use pi directly. So that's why you're having. So if you use pi directly, what do you have? If you use 3.14, what do you have? Okay. Our advice is use pi directly. It's on your calculator.
Shift and
See pi here. Shift and this x 10 raised to the power this. So use pi directly, please. So you'll be fast. Because you might not remember that 3.14 in the exam pressure. Just type pi. Shift pi. You will say something after. Correct. I was expecting you to correct me, but everybody just left it like that. There's a mistake somewhere. Watch. What he said is that are we not supposed to do it like this? Take note. They ask, are we not supposed to do it like this? 5 d squared over 4 minus 5 d squared over 4. This is what you ask, right? Yeah? You say yes or no, how? Are you confused? I am putting your balance and punch and see what you got.
You can still do it like that, but like the square, because I'm going to write 2 square, not 2
If you expand this thing now like this, it's square. It's the same thing. It's which of it are you using?
Wait,
I am doing the lesson. I like the confidence. Another person. It's the same thing. If you want to make it to punch, it's the same thing, bro. Punch. You say 220 square, right? You give us 480. 220 square. Let me write it down somewhere. You say this square, right?
4,800.
220 square. You give us what? 48400. And we have 170 square as what?
2,900.
2,900. Yep. Abi?
2,900. So minusing both of them. So we have what? If you minus both of them, you have 19500. Now put this 19500 inside and check your answer. So you now have 5 times 19500 all over 4, which is equal to what? 15315.266. Is what you're saying? So let's write it down somewhere. 15315.266. So now let's use that one and see.
Don't get out. 163.5.
550 minus 170 square over 4. So you're having a smaller value. Now do it this way. Do it this way. Let's see what you get. 15,000.
You got 15,350.
If you do it this way,
Yes.
like this one, I just
Yes. Yes.
Okay, well,
15,350.
So it's the same with that thing you were saying.
Yeah.
I see. So don't use this formula like this. Instead, use this formula. Separate it like this. I see. This value now is the correct one. Take note. If you just punch your calculator like this, it's going to give you a wrong value. Please take note. So separate it using this formula. Strike out this one. Instead, expand it like this. Because the pi is going to affect this one on its own. It's going to affect this one on its own. But if you put it here now, this pi is just one. Except you square this one and square this one. Like I'm not assuming like you want to use this formula. Except you square it. But if you're just leaving it like this now, use this one, use this way. This way, I see. Use this formula. Or you can expand this one and use times square and square. You get? But I prefer you use this one instead. So let's clean this and use this formula. Let's take. This is your own calculator, right? This is your own calculator. Thank you very much. Okay, Daddy. So let's clean this formula. We are still subtracting the internal diameter from the external diameter. We are subtracting the internal diameter from the external diameter. So this now is going out. So if you do this, I'm on my hand there. Regulating dust. All the time. That's why it's called class. So if you do this, now the pi what? 220 square over 4 minus 5 170 square over 4. This will give us 15,000 what? 315.26. So area of cylinder you want 15 what?
26 meters.
26. And then two decimal place, please.
Yes.
26, right? 26 meter square. Alright, we are making progress. So now look for the stress in both of them, right?
Yes.
Can I clean this one? I should clean them. Let me clean it from under.
Yes.
From under here. I put it here. Please take note of the two areas. Area of cylinder. Our force is not changing. The force is 1,900 kilonewtons. Now we record the formula for what? Stress. They say we should find the stress in both of them. Stress in steel, stress in area, in cylinder. So stress in steel. Because it will become what? The force over the area of what? Steel. And the force is what? This one here, 1,900 over the area of steel, that is 22 what? Call it 26 what? 98 point what? 01, punch this, punch this, punch this, punch this. While I do that, we also do the stress in cylinder, the punching that one. There's no time. Which will be equals to what? 1900 over the area of the cylinder, that is 15315, 15315.26. You see this thing I'm doing now, this is how it will feel like when they tell you 15 minutes more inside exam hall and you never could finish. Or you have not written finish, you have not finished writing. You start writing as if they are chasing you. That's why you have to read. Because even the person you are coming from, you're not sure if it's correct. You get? So please try and help yourself and read.
So the first one is 0.08.
0837.
0.4
0837.
0 what?
84.
0.08, 2 decimal place. And what's our symbol? You know why, right?
Yeah.
What about the second one? Please confirm the answer. 0.124. Thank you. 12. Kilowatt. Newton per watt. Millimeter square. So we are done with what? Part A. Part A, that's to find the stress in steel and the stress in what? Cylinder. You said no, why? No, we're not done with the question. So proceeding to the next part of the question.
Temperature is compressed.
They say we should do what? Read the second part, the big part. That's the final part.
The temperature of the compressed composite bar is reduced by 120 degrees Celsius.
Alright.
No change in length is allowed. Complete the final stress in the bar and cylinder.
Alright, complete the final stress in bar and cylinder. So now what's the formula for thermal stress?
Thermal stress is, yes, that's the
Check for your notes. It's alright.
Young body
People are not yet. You say what?
Epsilon.
Epsilon what?
So the young brother was applied by Axial, by thermal spirit.
Right? But now they gave us for steel. So this is the epsilon steel and this is for what? Steel. I see this. So now just substitute and get your answer. Now the what? Your modulus of steel is what? 200 watt, kilowatt, Newton per millimeter square times what? For steel.
0.00.
0 what? 0.001 times what? The one they gave me the question, please, what's it? Temperature they gave me the question.
120 degrees.
Times 120. Please pause and give us our final answer.
0.29.
That is what?
0.29.
0 what?
29.
See, never stress is zero. 0 what?
29.
29. So what will be simple?
So I was thinking individual steel and the aluminum cylinders before using to take their stress.
If we check the question, we'll tell you that the both of them will reduce in the same size. Check, read the question.
If the bond and cylinder contract by equal amount.
Equal amount. And for them to have equal amount, that is what they have equal force. Remember, I told you from Hooke's law, force is what proportional to what extension. So if it's equal force, causing the extension, so you have the same force, the same extension. So you're not changing any force, it's the same force, right? You get my point? Alright, so let's proceed. So this one, 0.29 watts. That's all, 0.29, right? So what are units? This is in what?
Okay.
This is in kilonewton per what? Millimeter square. This is 1 over Celsius. Let me show you now. This is in kilonewton per what? Millimeter square times this one now is in 1 over what? Celsius. Times this one is just in what? Celsius. This will cancel this. So if you let it what? Kilonewton what? Per millimeter what? Square. So that's what your symbol will look like. So let's proceed to the final one. This is the thermal stress in what? Cylinder. Which will be the same thing. Epsilon in what? Cylinder as EC. That's aluminium. Cylinder is made of aluminium. So let's write aluminium. AL times in what? Alpha in aluminium. That's the linear expansivity in aluminium. Times what? Change in what? Temperature. So what as what? Equal to what? This is what? 80 kilonewton, right? Times what?
0.000005.
How many zeros?
5
Times what?
times what?
120.
So you are seeing it, so that's substituting. So give me the final answer. 0.05. Because what?
0.05 kilonewton square.
Alright, thank you all for staying to the end of today's class. If you enjoyed today's class, just let me know in my DM. You have my numbers, right? If you don't have my number, please, I'll write it on the board, save it up. So I can share you the group link and you join the group. Send me, I need your feedback on today's class so I will know how to improve the next class. You get? Very important, feedback. Also, if you have any other challenge in any other topic or you need a private section, 1v1 section, also let me know. If you also want to learn AutoCAD and you have a system or you don't have a system, you want me to provide a system for you to learn AutoCAD, also let me know.